I want to talk about different things that we can use that have scalar and vector numbers associated with them. So the first question that I want to consider is I want to think about the question of how far does an object move, knowing that now we know that there are two different kinds of numbers. There are scalars and vectors. So what that means is that if I ask you how far do you travel, there's a different answer whether you're talking about it being a scalar or a vector. What I want to do is you can just continue this from your notes from a moment ago. But I want to imagine a set of axes, right? So I'm going to say I've got an XY axis, but I'm really interested in the X more than the Y, so I'm going to make it bigger like this. 4, 5, 6, 7, 8. So I'm gonna label this in meters, right? 2, 4, 6, 8. This could be measured in meters. Now I want to imagine the basic idea, right, is let's say that I start here at 4 meters, and let's say I walk 4 meters forward, 1, 2, 3, 4 meters forward to here, and then I turn around and I walk 6 meters back. So I walked 4 meters forward and 6 meters back. Now, if I asked you how far did I travel, what would you say? Go ahead, Anna, what would you say? Okay, negative 2 meters is a valid answer. Right? Because I'm 2 meters behind where I started. Is there another valid answer? Yep. 10 meters. How'd you get that? 4 meters forward and 6 meters back. So you add it all together, and you might have gotten 10 meters, right? I think those are both valid answers to the question, how far did I walk? Right? And this is where the difference between a scalar and a vector comes in, right? Of those two numbers, only one of them can be a vector, probably. Which one is probably the vector, the negative 2 or the 10? Negative 2. Why negative 2? It shows direction. That negative is telling me something about direction. So, just like that video you watched of Vector the villain, right? Vectors have two things, magnitude and direction. The way, at least right now, for this first chapter, which is actually chapter 2 in your book. For chapter 2, we are going to be thinking about vectors. The direction of vector means whether it's positive or negative. If it's positive, it's moving forward. If it's negative, it's moving back. So these have two very distinct names. So in physics, we're going to refer to, if the answer was 10 meters, we're going to refer to that as the distance. And the symbol for distance is just d. So the distance traveled in this case was 10 meters. But there's another word that we're going to use, which is the vector form to the answer how far, and we call that displacement. And displacement has a different symbol. The symbol we're going to use is delta x. Anyone seen that delta before? What does it mean? What's that? Change. Yes, delta means change. So if I say delta x, what I'm really saying is the change in x. And x is my position, right? So wherever I'm at along this axis, right, I'm calling that x. And displacement, the delta in this displacement, the little triangle, this is a symbol that just means my change. So the way I'm going to write this mathematically is I'm going to write it as an equation. I'm going to say delta x is equal to x minus x naught. And that's a little 0 next to the x. So this is going to introduce you to a new bit of notation that we're going to use. So this, first of all, if you hear me talk about something called x naught, I'm using the word like this, N-A-U-G-H-T. It actually might be N-O-U-G-H-T. I think it's N-O-U-G-H-T. what does that mean? The x0 means my, it's a way of saying my initial position, right? Because 0 means at time 0, where was I? So usually in physics, we're going to use the convention that if I say x with nothing next to it, that's your final position. And I'm going to use x with a 0, or x naught, as an initial position. So the displacement is always going to be my final position minus my initial position. So my final position was what? I ended up at 2, and I started at 4. So that's how we get, that's mathematically how we get this answer of negative 2 meters. All right. And again, just to be clear, this displacement is the, what should we say, the scalar or the vector form? The displacement is going to be, because it has a negative, it's going to be the vector. So this is going to be the vector form, and this one's going to be the scalar form. Now, you learned in what you just did, right, that we have two answers to the question of how fast we're going, right? We have the scalar form to the question how fast we're going, which we call, what was the scalar version of answering the question how fast? Speed. So we have speed, and we have velocity. And I'm going to give equations for these. So speed, we're going to define as S, and I'm going to use this term a lot. It's a triple equal sign. Anyone seen a triple equal sign before? You know what it means by any chance? Basically, it's the equation, so it's a stronger statement than equals. Equals means that they just happen to be true. The way I say it, there are different ways, but the way in physics I use the triple equal sign is I'm going to say it's defined as, right? It means that it's not just that speed happens to be equal to what I'm going to say. It means that the definition of speed is what I'm about to say, right? So a triple equal sign means it's defined as. So my speed is going to be defined as the distance I travel divided by, this is something called the time interval, but I'm going to call it delta t. It's the same as delta x, right? It means if I started measuring at 2 seconds and I went to 4 seconds, now that's that again, 2 seconds to 5 seconds, right? My delta, my change would be 3, right? So that's the definition of speed. So speed is going to be the distance covered divided by the time interval. And velocity is going to be defined as the displacement covered, which is delta x, divided by the time interval. All right. So the lie I want to clear up for you is this is not true. Speed itself is not equal to distance divided by time. What is equal to distance divided by time? Well, velocity is displacement divided by time, but even that's not true. What kind of velocity can I say that is true about? Well, it's actually the average. And the way I'm going to indicate average is I'm going to put a line over it, right? So S, and if I label that, if I were to read that out, I'd call it S bar, or I'd call it V bar. So V bar means the average velocity, right? We are never really measuring things at instants, right? We can measure the time it takes to go a distance, but we can't really measure an instantaneous velocity, even if we know that there is a such thing. Your book uses a term that I just want to explain. And is anybody in calculus right now? Okay. So if you're in calculus, this may, if it's not familiar to you yet, it may be familiar to you in the next few days. But there's something called a limit. So we're going to call the instantaneous velocity, which is v without a bar. So v bar is average velocity. The instantaneous velocity we're going to define as the limit as the time gets closer and closer to 0 of delta x over delta t. Now, if that confuses you, I don't want you to get hung up on that. I just want to explain it real quick. And just know we're not doing calculus in here. But the idea here is, what is instantaneous? How long is an instant? It's as small as you can imagine, right? A second is more than an instant, right? A half a second is more than an instant. If I talk about an instantaneous velocity, I mean the velocity at a very teeny tiny point in time. This is an abstraction. There is no way to measure that. But we can get closer to it. What this idea of a limit means is it means the shorter and shorter that we make our measurement of velocity, the closer we are to the instantaneous velocity. And then what a big portion of calculus is it's dealing with these infinitesimally small times, right? It's saying, okay, we take a real thing that has a real amount of time, and we shrink it until it's basically 0. What does that mean, right? That's the idea of instantaneous velocity. Yeah. Questions so far? All right. What I would like to do is I would like to finish today off by doing 2 practice problems, and then we will be done. Before I do a practice problem, I'd like to introduce to you what's going to be our problem-solving method, which may seem to you at sometimes, it may seem to be a little bit cumbersome as the problems are easy here at the beginning. But if you get used to using this problem-solving method, as a matter of fact, you're going to think it's overkill to do the problem-solving method in the first practice problem we do. But the second practice problem, you'll see that it would be really difficult to solve without it. Right? So let me tell you what the problem-solving method is for this class. I'm going to get another sheet of paper. So I have a 7-step problem-solving method. Step 1 is draw a picture. This is the one that sometimes you'll think is overkill. But what I want to remind you as we go on is this is physics class, it's not math class. What does physics mean? Physics means that every bit of math we do has a physical meaning to it, right? And so one of the things is we're going to kind of get, and when I say picture, I don't mean an artistic picture. I mean like a diagram that kind of connects what we're doing to the physical world. The second step is going to be what I call to set up your knowns and unknowns. You may have done this if you had chemistry, you may have done something like this. The third step is make sure units are the same. Fourth step is pick an equation. Fifth step is plug and chug. Sixth step is answer with units. I said it was a 7-step problem solving method. I lied again. It's 6 steps. Okay. First example problem. Find the time it takes to go 150 kilometers at 23 meters per second. Algebraically, this is a trivial problem, right? You can all solve this pretty easily. I want to kind of break down the process. So we're going to imagine that we are in a car. So step one is draw a picture. We're going to imagine we're in a car going at 23 meters per second, and I'm traveling 150 kilometers. That's a picture, right? It's nothing fancy, but it connects what we're doing, what we're solving, right, to a physical reality. We got a car traveling a distance. Step two is knowns and unknowns. What I mean by knowns and unknowns, another way of saying this is we want to translate the problem into math. So I've got a problem in English, I want to translate it into math. So if I think about this, what is 150 kilometers in this case? It's the distance, and you could solve it doing the distance. I'm going to solve it like it's a displacement. But you could also say distance. I'm going to say delta x is 150. In that case, 23 is what? That's a speed or a velocity, right? And I'm trying to find how long, so I'm trying to find a time. Good question. Since I'm staying the whole time, I'm gonna treat this as an average. With the second practice problem, which we probably won't get to today, we'll get to the difference. But now let's just say average. Okay. Now, so I have my knowns and unknowns. The units are not the same. Which unit should I change? Probably the easiest thing to do. It's probably easiest to change this. And if I change my delta x, if I change my delta x, right? So you've done this sort of thing before where we say 1 kilometer is equal to 1,000 meters. So it's 150,000 meters is the delta x. Step 4, we're going to pick an equation. Obviously, we're going to pick this one. But let me show you the way that I prefer that you solve it. Now, at this point, you could plug in and you could solve it. But you're going to find it's going to be easier if I solve this thing algebraically first. So what I mean by that is if I solve for delta t, right? How would I do that? Well, if I multiply both sides by delta t, I would get delta t times v equals delta x. So that means delta t equals delta x over v. Questions about how I did that? Now I want to show you why I did that. I did that because if I take 150,000 meters divided by 23 meters per second, and I'm just going to solve that for you real quick because I want to make sure to finish this. I get 6,521 seconds, right? And if I wanted to, I could get that into hours or something. But I just want to show you something real quick about the units. If I take a meter divided by a meter per second, watch what happens to the units. The meters cancel, and then I have a 1 divided by a 1 over a second, which is equal to what? A second. So one of the cool things is the unit should always work out. We didn't get quite as far as I thought we would today, but we will finish next time. You don't necessarily have any homework to deal with because of that.